And here we're going to see a nice rule, which is L'Hopital rule. And something that happened while we worked on this is when we worked on the limits were helped us to achieve the derivative, right? So now what we are going to do is the derivative is going to help us find the limits, right? So that's a very useful, and I've seen students use this even earlier in early stage. However, there may be some problems if L'Hopital rule does not apply. So in this presentation, we'll define in which cases it applies, which cases it doesn't apply, and which cases you can just pursue what you already learned. You don't have to use L'Hopital rule. Now, of course, some, when they needed to use it, they used it, and that's fine. So we're talking about indeterminate forms, and indeterminate forms are something that they are not obvious forms. It's almost like the undefined style. So when you're working with these forms and these in summary, L'Hopital rule starts with these two, and you can figure out the others from it. So if you have 0 divided by 0 for limits, then it's an indeterminate form. Or if you have infinity divided by infinity. And of course, from there, we can find these other forms that, let's say, work against each other. Infinity minus infinity, 0 to power 0. Infinity power 0, 1 power infinity, and 0 times infinity. So these are the indeterminate forms. And L'Hopital rule applies if you have that case. And so we'll start with these first two as the basic way in which L'Hopital rule started and expanded. If you have a limit of a function as x approaches a and is 0, and the limit of g of x as x approaches a is also 0, or for the infinity case, which means you have an indeterminate form when you do f divided by g. So 0 over 0 or infinity over 0, infinity over infinity, then in that case, the L'Hopital just says that the derivative of this quotient is same as the derivative of as the quotient of their derivatives. And of course, there is a proof to it, a little long, but there is a proof that this is correct. And this depending on the limit, this right side, this f prime divided by g prime limit exists. So the condition, of course, is you have to have indeterminate form and this right side limit exists. In that case, you can easily apply L'Hopital rule to figure out the solution. So this is the other indeterminate forms that that were mentioned, and how do we resolve these? So the question would be, okay, if L'Hopital rule addresses the first two, how do you resolve the others? Well, if, for example, you have negative infinity minus infinity or 0 times infinity, you're going to write the product or the difference as a quotient and apply L'Hopital rule. So you will trick this form to another equivalent form in which you can use L'Hopital rule. For 0 power 0, infinity power 0, 1 power infinity, and these, you can change to like a product or a difference, to apply L'Hopital rule. So here we use just like we did in the past. You remember that logarithmic differentiation where we used the log in order to simplify things and be able to find that derivative. So we did that in the past. Similar thing here. We're going to take the function or whatever we're looking for the limit, and we're going to take a natural log to transform the problem to a form in which we get that type of 0 times infinity. So if you get 0 times infinity, then you can go back to this one, right? So this concludes everything when it comes to L'Hopital rule, but of course it takes practice to get used to which one is indeterminate, which one is not, and what to use. And as a summary, if we have these are indeterminate forms and we have the other forms, so what's not, indeterminate, let's say 0 divided by infinity, and we'll talk about these in examples. These forms do not require L'Hopital rule. And these forces, they kind of work together, as you see here, against each other, but here infinity add infinity, you just keep going to infinity, becoming larger. So that's not an indeterminate form. And this is kind of a summary to note. So let's see a few examples and we do some from the homework. Let's say we have this limit as x approaches 1 for ln x over x minus 1. So if you usually, we use the quotient rule, we say the limit of ln x as x approaches 1 divided by the limit as x approaches 1 of x minus 1. Then when you substitute for here, you can substitute the limit of 1 is 0, and the limit of here, direct substitution, is also 0, 1 minus 1, and that gives you 0 over 0, which is indeterminate form. Remember, for L'Hopital rule, if you have 0 over 0 or infinity times infinity, then you can use L'Hopital rule. In that case, we need the derivative of the numerator and the derivative of the denominator. This is a common derivative, which is 1 over x, right? So which you have here. And this is just 1 minus 0. So it transforms to 1 over x. When you use a direct substitution, you get 1. Now, when for an indeterminate product, the other case where we say you have to kind of trick it, so we can deal with it by writing f times g as f divided by 1 over g. So let's just do this. This is a small number example. So it's not really, the functions. So 5 times 6, right? It's 30. So if we do 5, something like this, is this incorrect? No, we actually have done this all the time. It's just now we do it kind of reverse way. So what is 5? It's 5 over 1. You do that keep change flip, or you keep the first one, you multiply by the reciprocal of the second one, and that's the same thing. So you do this for functions. Or you can do the other one, you can switch the other. If we look at this example, and if you sketch, for example, ln x, and this is x and y, and 0, approaching 0 from the right side, then the limit as x approaches 0 from the right side is going to be negative infinity. So we have the limit x approaches 0 from the right side of x times the limit of ln x as x approaches 0 from the right side. This is negative infinity and this is 0. And if we look at, you'll see that it's an indeterminate form there. So what we can do is, this is a product, right? And as you see in this method here, that write the product or the difference as a quotient and apply the L'Hopital rule. So we need to switch one to a quotient and we'll use L'Hopital rule. So here we took x, just like I did for the numbers. So x is 1 over its reciprocal, because x is 1 over x, and we can show that this is correct when you do keep, change, flip, or multiply by a reciprocal. This is x. So you take one of them. You can do either one, but let's say we take x, we rewrite it as that. So x times so x ln x becomes 1 over x ln x. And of course, this is when you do the fractions, that's ln x over 1 over x, which so the simple direct way, if you have this, you just bring 1 to the denominator as reciprocal. So that's a simple way of thinking about it. You can't, of course, you can't switch it. You can't say ln x over x, because that's not same as ln x times x, right? So bring one of them to the denominator as reciprocal. When you do that, now you have because 1 over x, the limit as x approaches 0, that's going to be, if you look at it again, it's going to be infinity, but even precisely, here is 1 over x. That's why it's good to know these basic functions and how they graph. These are from, algebra, and we talked a lot about these functions when we did limits and so forth. So you need to have that picture in mind, or set, or take an algebra book, a sheet with the basic functions, and when you look at them, you'll see. So approaching 0 from the right, that goes to infinity, right? So this is infinity. And we did the other for ln x, that's also infinity. So you have an indeterminate form, and we can use L'Hopital rule. And we do the derivative of ln x. The derivative of this one is 1 over x. That's a common derivative in that table. And 1 over x, you can use a reciprocal or use the quotient, whichever you use, you're going to get negative 1 over x squared. It's the reciprocal form is negative f prime over f squared, or if you use the quotient, you get that. So now you simplify these two. So let's separate these notes. So 1 over x, negative 1 over x squared, it's same as 1 over x times x squared or negative 1. So it's x squared over negative x, which is negative x. And direct substitution, that's a 0. Indeterminate differences, Here is an example for it. We have, you see that that indeterminate form. If we look again, same way as the other examples for ln x, it's approaching now. Let's show it again. You know, this is, you see now this natural log function, we've done it so many times. It's useful to know this one, exponential function, all those basic functions to know how they graph. So this is a 1. So approaching 1 from the right side, that goes to 0. So limit ln x approaching 1 from the right side is 0. So when you do 1 over ln x, it's going to be infinity. So that's infinity. Similar, this one is a direct substitution. It's easy. 1 minus 1 is just 0. 1 over 0, infinity. So this is indeterminate form. So what we do in this case, let's show you here again in the notes. If you have this, write the product or the difference as the quotient and apply the L'Hopital rule. So putting these together, we have x minus 1, right? Common denominator minus, so you do a common denominator. Ln x, and here x minus 1, x minus 1. So that gives you x minus 1 minus ln x, right? So that form there. And when we do this form, both numerator and denominator have a limit of 0. So when you check this again, you'll find out that both are 0. So L'Hopital rule applies because it's an indeterminate form. And because it's an indeterminate form, you can do that f prime over g prime, and you do the derivative of the numerator and the derivative of the denominator. And of course, you keep the differentiation rules that we did, like in here, the product rule. This is just a 1 and the other is 0, and this is 1. So you just follow the differentiation rules until you get that simple form. And when you do that, you'll find that you can apply the direct substitution. So there is another case which we looked at with these indeterminate forms, which is the power rule, or the power form of the indeterminate form, where it happens that if you have this power, you run into something like this or this or this, which is the other indeterminate forms. And when we run into this, there is something that we've done in the past, which is that, for example, logarithmic differentiation. We took natural log to both sides so we can benefit from the properties of log and be able to differentiate, right? So it's a similar idea here. We're going to use the log. The process is going to be, if you want to find this limit for y, and it looks something like this, right? What you can do is take the log to both sides. That will allow you to switch the power to a product, you see. And when you do that, it's going to give you that indeterminate form, but you will need to reverse it back. So that's the important part, because this is the request. You do this in order to have and be able to use L'Hopital rule, but you need to go back to the y, because you'll be asked for the limit of the y or this function. right? Not the natural log. So we do examples, and there is one in the notes or from the text. If you investigate these two, you'll find out that, for example, as x approaches 0 from the right, sine of 4x is just 1 because that's 0. 1 plus 0 is 1. And the cotangent is approaches infinity as x approaches 0 from the right side. So you get 1 to infinity, which is an indeterminate form. So what we do in this case, we wait for a minute and we forget about the limit there. We just say, let's deal with the this part here by itself, this y by itself. And you take a natural log to both sides. When you do that, we know this power rule for the log, it allows the cotangent to come to the front as a multiplication, right? So it switches it to a multiplication. And when you have a cotangent, it's same as 1 over tangent, that reciprocal identity there. So what we have now is ln 1 plus sine 4x divided by tangent of x, which allows to use L'Hopital rule. And this is a chain rule, right? The log with a chain rule, the formula we did, which says f prime over f. So this is, and the f, when you have ln f, right? So this is the derivative, and this is the inside, this is the f prime over f. And the derivative of tangent is just secant square. No need to use a chain rule, it's just the basic common derivative there for tangent x. We don't have f. If we have f, we'll use the chain rule, but we have just x, and we differentiate with respect to x. So when we do that, now you can use the 0, and you'll find it's 4. Yeah, so as you see right now, the step, we're given this, so we call this as y, right? And to do that, we use the ln y. So we need to go back to y. To go back to y, so you can do 2 steps. So step 1, take ln. Step 2 is to reverse it. Step 2 is take e to ln to reverse it, which is this one. All right, so that makes the final answer e to power 4 and not 4, right? So because the 4 is for ln y, where we want the limit for y. So let's look at some examples here from the homework. So we need to summarize everything that we did. I begin with this cases here. So let's say that we have these limits as x approaches a. So let's discuss some cases. So for example, what is the limit as x approaches a for f of x or g of x, which, you know, you do this usually. And we know the limit, this is one of the limit laws. And so the limit of f of x is 0, and the limit of g of x in this case is 0. So this is an indeterminate . and I'll probably just do something like this for abbreviation, indeterminate form. Right, so you pick indeterminate or you type indeterminate form for this one. So just so we become familiar with it, so maybe we call this A. So B is limit x approaches A of f of x over p of x. Similarly, when we use the limit law for f of x, we're going to get 0. For p of x, we're going to get infinity. And if you look at the notes again here until you get used to them, 0 over infinity is not an indeterminate form, and it's not required L'Hopital rule in this case. Why? Let's go back to it. Why? Because you have, you know, you almost have like something like this, where 1 over infinity is 0, so you run into something like this, where a number or 0 you divide by infinity for the limit. That means when you divide by infinity for the limit, it's becoming too small. It's approaching 0, so you're having 0 times 0, so that's just a 0. The next one, h of x over p of x, h of x is 1, and the limit of p of x in this case is infinity. That's same as now on 0. Then when we have limit as x approaches a of p of x over q of x, p of x is infinity, and that's the limit is infinity. So this is another indeterminate form, right? Let's try, for example, the product. We'll follow the same thing. So let's show the first one. Let's say we have, we need to find the limit as x approaches a for f of x times p of x, which you used, you know, if you use the limit law, for f of x is 0, for p of x is infinity. That's indeterminate form, right? So similarly, if we need h times h times p, the limit is 1 for h, and the other limit for p is infinity. 1 times infinity is infinity, not indeterminate. And the limit of x approaching a, let's say p times, now we do the other one, q. So the limit here is infinity, and q is infinity. So you see, so this is not, this is something becoming too large. Infinity times infinity is something that's increasing and becoming way too large towards infinity. So that's just going to be infinity. And, you know, and you can always look into the summary of the notes, which ones are determinate and which ones are not, or the other way, which ones are indeterminate and which ones are not. So let's look at in this example for the quotient, and here, of course, or probably these for the power. Let's see, do we have a few more? I think in these you want maybe to look into the powers, right? Yeah, so let's do that for number 3. So let's do, if we want the limit as x approaches a for f of x, and you have a g of x. So what happens in this case, you're running, maybe I'll just put something like, you're running into f of x is 0 and g of x is 0. So that's an indeterminate form, right? So that's what pick for the answer. And if we're looking for the limit of f of x as x approaches a, p of x, and now we have f of x is 0 and p of x is infinity. In this case, we can switch it. Remember here, 0 to infinity, infinity to 0 as powers, 1 to infinity. So the powers, right? And we just did a long example on it. Maybe we need to switch these this way. Then we're going to say, let's take the function f of x, power p of x, call it the y function. Then we need to take a natural log, the ln, to both sides. When we take ln to both sides, it will allow us to switch this to the product. Right. And now we can see that when x is near a, p of x approaches infinity, right? So this is given, p of x approaches infinity, right? And ln of f of x will approach negative infinity. So look at this one here on the side. If you have the limit of a function as x approaches a, approaches 0, right? Then if the function approaches 0, right? So think about for the ln f of x and look at the graph that we did before again. Right, so that's going to be towards negative infinity. So keep in mind that graph of ln and x when it approaches 0, right? And you will see that it's going to be approaching negative infinity. And of course here it's going to be approaching a from one side, right? So the natural log here of this one, in terms of limit, talking about in terms of limit. So here maybe we should say in terms of limits, what happens? One goes to infinity, one times negative infinity. This is not an indeterminate form. This is negative infinity. So this is ln y limit as x approaches a is going to be negative infinity. And now we need to reverse this. So remember that step 1, you take ln to both sides. Step 2, you need to reverse it. It's like you're going to do the e to the answer. So the limit as x approaches a for e ln y it's same. So think about it now as what is e to negative infinity. So maybe I need to put a graph or something to make it. And this is one of the ones, of course, that are some of the basic functions that everybody needs to know how to graph. The ex is an exponential function. E is bigger than 1, so it's going to grow. And so it's almost like here you're going to do e to negative infinity. It's almost, that's what we're doing when you do that to both sides, right? You take it to both sides. So this is the form. So as maybe we do this way. So as e approaches negative infinity, you see that the function is approaching 0 because this is a horizontal asymptote and it's trying to reach that 0 there. So so 0 will be for this one. So it looks like maybe look like a simple thing from the beginning, but we're running to 0 power infinity, which means we need to do an ln to both sides. Once we do ln to both sides, we'll find out that the answer is negative infinity. And few things here are useful is this thing here, to know the natural log function, the ln x. Right? And also to know this one here. What else? So we can look as well at another form. So for example, the limit x approaches a of h of x, p of x. That's gonna be, if we look at this, h of x is 1 and p of x infinity, so that's indeterminate form. D, let's say we want the limit x approaches a for p of x, f of x. So this is, we're looking at the limit of p of x is infinity and f of x is 0. That's also an indeterminate. In this example, it looks like we've done this in the past. You know, if this can factor, then why not just stay within the easy way, and the direct substitution is 1/12. But can you use L'Hopital rule so that you can investigate that and you can take the derivative and you find 1/12? But in some cases, let's say this one here, you know, we need to know how the cosine, what is based on that unit circle, pi over 2, cosine starts 1 here and it goes to 0, right? So, and this is a direct substitution, 1 minus 1, so 0/0. So this is indeterminate form. And if it's that we have to see if the other right side limit exists, then we can use L'Hopital rule. But it is indeterminate form, so we can start with L'Hopital rule, and here it says use it. So we need the limit x approaching pi over 2 from the right side, the derivative of cosine, and the derivative of minus sine, and that's going to be negative sine, and 0 minus, this is cosine, and negative by negative is positive. So it's limit of x approaching pi over 2 from the right side of tangent x. So here it's going to be helpful to know, how the tangent function looks. So it repeats this pattern. So from the right side here of pi over 2, it is approaching negative infinity. For this question, they say use L'Hopital rule, but but where appropriate. So yeah, so L'Hopital rule does not apply here. So here we'll say it does not apply because when you investigate this one with the graph we did for ln x, it's going to negative infinity and 0. So it's not, it does not apply. So it just means you're dividing. So think about it now in terms of limits, right? Think about it in terms of limits. You're dividing negative infinity by a small. As this approaches 0, the numbers is getting too small. So negative infinity is just going a little more towards it. Negative infinity just becoming kind of bigger towards infinity in that sense. So this one just is going to be negative infinity, right? Because L'Hopital rule does not apply here. So we go into that sense of what we did in the beginning. Similar here, if we need to use L'Hopital or not, but remember elementary method, that's if we have that, why not? And that's what we need to keep in mind. Not just because when we learn something new, it means now that it takes over. We need to identify where each one is can be applied, and this is a 5, so this is limit of x approaches 1 of x plus 5, so this is a 6.